Hello friends, in this video we shall learn Rolle's theorem. What is the statement of Rolle's theorem? Statement of Rolle's theorem is like this. If fx is a continuous function in closed interval ab, fx is a derivable in open interval ab, and functional value at a equal to functional value at b, that is fa equal to fb. That means if a function satisfies these three conditions, that is, the function must be continuous in closed interval ab, it must be derivable in open interval ab, and f of a equal to f of b. Then there exists at least one value c in the open interval ab such that f dash c equal to 0. We shall prove this theorem. Fx equal to 0 for all x. Then f dash x is also 0 for all x, and hence f dash c equal to 0, and hence theorem is satisfied. Second, if f is a continuous in closed interval ab, it is a bounded and attains its maximum capital M and minimum small m, say at two numbers c and d. That is, maximum m is at point c and minimum m is at point d, lying in between a and b, such that f of c equal to m and f of d equal to small m. Then case 1. Case depends on this capital M and small m. Capital M and small m are equal, that is fc and fd are equal. Then f is a constant function, so that f dash is 0 for all x in AB. If maximum value of the function and minimum value of the function is same, then function is a constant throughout. Function has the same value throughout, and hence that function is a constant, and we know that derivative of constant function is 0, and hence f dash is a 0 for all x in open interval AB. Case B, if m is greater than m, that is the maximum value is greater than minimum value, then m equal to f of c. F of c is greater than f of c plus h. That means functional value at point c must be greater than functional value at all other points except c, for the values of h both positive and negative. Then f of c plus h minus f of c, this is less than 0. F of c plus h minus f of c, this is less than 0, and therefore as h is positive, f of c plus h minus f of c, this value is less than or equal to 0, and f of c plus h minus f of c divided by h is greater than 0 for h is less than 0. If h is greater than 0, then this value is less than or equal to 0, and if h is less than or equal to 0, then f of c plus h minus f of c divided by h is greater than or equal to 0. Second condition is f is differentiable. Since f is differentiable in open interval AB, and from 1 and 2 as h tends to 0, we have f dash c is less than 0, and f dash c is greater than 0. This from this, as h tends to 0, from this f dash c is less than 0, and from this f dash c is greater than or equal to 0, and hence as f dash c is less than or equal to 0 and f dash c is greater than or equal to 0, this implies that f dash c equal to 0 for some value c in AB. For at least one value, f dash c must be 0. Similarly, if small m equal to f of d, which is less than f of d plus h, small m is minimum value, therefore f of d is less than or equal to f of d plus h for values of h both positive and negative, we follows that f of d plus h minus f of d divided by h is greater than or equal to 0 for h is greater than 0, and f of d plus h minus f of d divided by h is less than or equal to 0 for h less than 0. As h tends to 0, From this, we can conclude that as h tends to 0, from this, we can conclude that f dash d is greater than or equal to 0. And from this second, as h tends to 0, we can conclude that f dash d is less than or equal to 0. And hence, f dash d equal to 0 for at least one point d in open interval AB. And hence, f dash d equal to 0 for at least one point d in open interval AB. This proves the theorem. We shall write some notes. Geometrically, Rolle's theorem states that the tangents at C1, C2, C3 are parallel to x-axis. See this figure? In this figure, tangent at C1 is parallel to x-axis. Tangent at C2 is also parallel to x-axis. Tangent at C3 is also parallel to x-axis. Note second, the function y equal to f of x equal to 1 minus x raised to 2 by 3. Fx equal to 1 minus x raised to 2 by 3 in minus exponential minus 1 to 1 is not differentiable at origin O. And as it does not satisfy the condition of Rolle's theorem, so f dash c not equal to 0 for any c in minus 1 to plus 1. See this figure. For any value of c in minus 1 to 1, f dash c is not equal to 0 is not satisfied. Why? Because it does not satisfy the condition of Rolle's theorem, that is fx is differentiable in minus 1 to plus 1. As this condition is not satisfied, f dash c is not equal to 0. We shall try to solve some example. In our examination, always questions are asked to verify the Rolle's theorem. Dear friends, we are uploading the videos on complete syllabus of first year engineering mathematics 1. So please subscribe the channel and don't forget to press bell icon so that you can get updates. We are also providing notes, all solve examples from the exercise. So please join the channel. Our first example is verify Rolle's theorem for the following functions: fx equal to x into x minus 2 into e raised to 3x by 4 in open interval 0 2. We know that f of 0 equal to 0. Why? F of 0 equal to 0 into 0 minus 2 into e raised to 0, which is 0. F of 2 equal to 2 into 2 minus 2, 0 into e raised to 3 into 2, 6 by 4, that is 3 by 2. This 2 minus 2 is 0, therefore f of 2 is also 0. Therefore, f of 0 equal to 0 and f of 2, this condition of Rolle's theorem is satisfied. F is continuous, clearly. F is continuous and f is also differentiable. Therefore, all the three conditions of Rolle's theorem are satisfied. And hence, by Rolle's theorem, we can conclude that f dash c equal to 0. We have to check whether f dash c equal to 0 or not. We shall derive fx. If we differentiate fx, we get f dash x equal to derivative of x1, x minus 2 into e raised to 3x by 4 as it is. Then x as it is, derivative of x minus 2 is 1 and e raised to 3x by 4 as it is, plus x as it is, x minus 2 as it is, and derivative of e raised to 3x by 4 is e raised to 3x by 4 into 3 by 4. Therefore, f dash x becomes x minus 2 e raised to 3x by 4 plus x e raised to 3x by 4 plus 3 by 4 x minus 2 e raised to 3x by 4. If we take e raised to 3x by 4 common, we will get x minus 2 plus x plus 3 by 4 into x minus 2, and which will equivalent to 3x square plus 2x minus 8 by 4 into e raised to 3x by 4. We know that f dash c equal to 0. F dash c equal to 0, this implies that 3x square plus 2x minus 8 equal to 0. This term equal to 0 because this exponential term will not be 0 and therefore this is 0. 3x square plus 2x minus 8 equal to 0. If we calculate this 3x square plus 2x minus 8 equal to 0. 8 into 3 is a 24. And if we factorize 24 in such a way that their difference is a 2, we can write 6 and 4 are the factors whose difference is 2. Therefore, we can write this as 3x square plus 6x minus 4x minus 8 equal to 0. From this, I can take 3x common. Therefore, x plus 2 will be there. From this second 2, I can take 4 common. Therefore, x plus 2 will be there. And from these two terms, bracket x plus 2 is taken common. And we will get 3x minus 4 in another bracket. We know that if product of two terms is 0, then any one term must be 0. Therefore, x plus 2 equal to 0 or 3x minus 4 equal to 0. If x plus 2 equal to 0, we can conclude that x equal to minus 2. If 3x plus 4 equal to 0, we can say that 3x equal to 4. Therefore, x equal to 4 by 3. And as we know that f dash c equal to 0, therefore this x must be replaced by c, and hence we get c equal to minus 2 or c equal to 4 by 3. But minus 2 doesn't belong to open interval 0, 2. But c equal to 4 by 3 belongs to open interval 0, 2. And hence Rolle's theorem is satisfied, because Rolle's theorem states that there must exist at least one point C in AB such that f dash c equal to 0. Thus, we have verified Rolle's theorem. Our second example is verify Rolle's theorem for the function fx equal to x raised to 2m minus 1, a minus x raised to 2n in open interval 0a. Here, f of 0 equal to 0, because if we put x equal to 0, we will get this 0 raised to 2m minus 1, that is 0. 0 into anything is 0, therefore this is 0. f of a, if we put x equal to a, this a minus a becomes 0, and we will get f of a is also 0. This last condition is satisfied. F of 0 equal to f of a. And f is a continuous, because this is a polynomial function. F is differentiable in open interval 0a. As all the three conditions of Rolle's theorems are satisfied, we have f dash c equal to 0 for some c in 0a. Now we shall differentiate fx. F dash x equal to, we shall use uv rule. This is a function u, this is a function v. And derivative of u into v as it is plus u as it is into derivative of v. Derivative of x raised to 2m minus 1 becomes 2m minus 1 into x raised to 2m minus 2, and a minus x raised to 2n as it is, plus x raised to 2m minus 1, this term will be as it is, and derivative of a minus x raised to 2n is 2n, a minus x raised to 2n minus 1 into minus 1. If we take some terms common, that is x raised to 2m minus 1 and a minus x raised to 2n, these two terms common, then there will remains 2m minus 1 divided by x minus 2n divided by a minus x. Now, by Rolle's theorem, we know that f dash c equal to 0. Therefore, in this f dash x, we shall put x equal to c, and we will get c raised to 2m minus 1, a minus c raised to 2n, 2m minus 1, 1 by c minus 2n divided by a minus c. This is equal to 0. This term will be never 0. F dash c equal to 0 implies that this term, as this is a multiple term, this term must be 0. That is 2m minus 1 divided by c minus 2n divided by a minus c equal to 0. This implies that c equal to a into 2m minus 1 divided by 2m plus 2n plus 1. How this can be obtained from this? Let us see. 2m minus 1 divided by C minus 2n divided by A minus C. If I multiply these terms crosswise, I will get 2m minus 1 into A minus C minus 2n into C cross multiplication. This is equal to 0. Now 2m into A, 2ma minus 2mc minus 1 into A minus minus plus C minus 2nc equal to 0. Now these three terms are containing C. Therefore, I shall transfer these two terms to the right hand side and I will get 2ma minus A equal to 2ma minus A equal to 2mc plus 2nc plus C. I shall take C common equal to 2m plus 2n plus 1 into C. And that's why C equal to 2m minus 1 into A is taken common divided by 2m plus 2n plus 1. This is the value of C. We know that C lies between 0 to A because this term is less than A and this term is not equal to 0. That's why C belongs to 0A and hence our Rolle's theorem is verified. Our third example is find the root or find the solution of the equation x ln x minus 2 plus x equal to 0 lying in open interval 1, 2. Solution. Choose fx equal to x minus 2 ln x, which is a continuous function and differentiable function in open interval 1, 2. And further, f of 1 equal to 0. Why? Because log of 1 becomes 0. And that's why f of 1 equal to 0. And if we put x equal to 2, 2 minus 2, this term becomes 0 and hence f of 2 is also 0. Thus f of 1 equal to f of 2 equal to 0. Thus, f satisfies all the three conditions of Rolle's theorem. What are the three conditions? F is continuous in closed interval, f is differentiable in open interval, and f of A equal to f of B. All these three conditions are satisfied by fx. And so, there exists a point C in AB such that C in 1, 2 such that f dash C equal to 0. Here, f dash x equal to derivative of this is, we shall use UV rule. Derivative of x minus 2 is 1 and ln x as it is plus x minus 2 as it is and derivative of log x is 1 by x. If I simplify this, I will get x ln x plus x minus 2 divided by x. F dash x equal to this. We know that by Rolle's theorem, f dash c equal to 0. Therefore, we get c into ln c plus c minus 2 divided by c equal to 0. If I transfer this to the c to the right hand side, I will get c ln c plus c minus 2 equal to 0. That means c is a root of the equation x ln x plus x minus 2 equal to 0. Show that the equation f double dash x has at least one real root, a real root between a and b if f dash f double dash are continuous in a less than or equal to x less than or equal to b, and the curve y equal to fx crosses the x-axis at least at three distinct points between a and b inclusive. We shall prove this. Let C, D, E be the 3 points where y equal to fx crosses x-axis. As they crosses x-axis, we will get f of C equal to f of D equal to f of E equal to 0. And we shall assume that A is less than C is less than D is less than E is less than B. The function f satisfies Rolle's theorem in two distinct intervals c to d and d to e. Function satisfies Rolle's theorem in two intervals c to d and d to e. Since f and f dash are continuous and f of c equal to f of d equal to f of e equal to 0, there exists at least one point in each interval CD and interval DE, such that derivative is 0. Let C1 belongs to CD, such that f dash C1 equal to 0, and C2 belongs to DE, such that f dash C2 equal to 0. Now the function f satisfies Rolle's theorem because f and f dash are continuous and f of C1 equal to f of C2. Therefore, by Rolle's theorem, there exists a number C3 in between C1 and C2 such that f double dash C3 equal to 0. Thus, at least one root C3 of the equation f double dash x equal to 0 lies in the interval AB. This is the proof. Example, without solving, show that the equation x raised to 4 plus 2x cube minus 2 equal to 0 has one and only one real root between 0 and 1. We shall assume that fx equal to x raised to 4 plus 2x cube minus 2, which is a continuous function because it is polynomial function. It is also differential function in open interval 0 to 1. There and f dash x equal to 4x cube plus 6x square. X raised to 4, derivative of x raised to 4 is 4x cube. Derivative of 2x cube is 6x square. Derivative of 2 is 0. If we take 2x square common from these two terms, we will get 2x square into 2x plus 3 equal to 0. This becomes 0 only when x equal to 0 or x equal to minus 3 by 2, because this bracket is 0 or this term equal to 0, both of which do not lie in between 0 and 1. Both of these 0 and minus 3 by 2 do not lie in the open interval 0, 1. Thus, fx equal to 0 for any x belongs to 0, 1. By Rolle's theorem, there do not exist a and b such that f of a equal to 0 and f of b equal to 0. That is, the equation fx equal to 0 cannot have two real roots. Further, f of 0 equal to minus 2 and f of 1 equal to 1 are the opposite signs, and fx greater than 0 for every x in 0, 1. Therefore, fx crosses x-axis exactly once. In other words, fx equal to 0 has one and only one root between 0 and 1. Dear friend, if you like this video and you want to watch the videos of similar type of all the syllabus of M1, that is Engineering Mathematics Paper 1, then subscribe the channel and don't forget to press bell icon. Thank you. See you in next video.